All right, I wanted to take a moment and look at the general equation of the tangent line to a function f at the point a, f of a. This is just the point slope form, which you've learned before. It's y equals f prime of a, there's your slope, times x minus a, and then I shifted the y1 over, and that's going to be plus f of a. And so that's a formula worth jotting down and making sure that you know, because you'll often be asked to write down the full equation of the tangent line. All right, so let's look at an example that we visited before, way back in 1.3. Man, it seems like a long time ago. We're going to go rock chunking. And like before, I'll just remind you that it's a very bad idea to throw rocks off of cliffs, because, especially high cliffs, because there might be somebody at the bottom that you don't know about. So, this is all hypothetical and theoretical. No actual rocks are being chunked. So anyway, we're throwing a rock off of the cliff, and the distance traveled by the rock after t seconds is given by this formula. This is capturing the fall of the rock. So 0 seconds, it's at the top. 1 second, it's 4.9 meters down, so on and so forth. So we're asked to find the velocity of the stone the instant 5 seconds have passed. And we played with this back in 1.3, and we even set it up in Mathematica, and we ran a bunch of computations, but we said this isn't actually computing it, this is just estimating it. And so let's look at what we did before. So before, we realized that the average velocity, I'm going to switch colors to help that make it easier to see here. Average velocity from t seconds to 5 seconds is, well, it's s of t minus s of 5 all over t minus 5. That's what we did last time, right? Average velocity. And so the point is, we said we were interested in the limit as t goes to 5. And so let's write that down. The limit as t goes to 5 of s of t minus s of 5 all over t minus 5. And this is the instantaneous rate of change at t equals 5. Now, what I want you to realize, though, is if you look back, I'm going to scroll up real quick, so don't get seasick here. If you look back at that other formula that we had for f prime, for the slope of the tangent line, okay, I'm using a different variable. I'm using t. This formula is exactly what shows up right here. This is nothing other than s prime of 5. And so the moral is, the point of this example is, the derivative of a function at a point, i.e. the slope of the tangent line at that point, that's what the derivative is, can be interpreted as the instantaneous rate of change of f of x at x equals a. And I want to give you a little bit more notation before we go on. So let's imagine we have this situation. I've got 2 points, x1, x2. I'm interested, by the way, I'm interested in studying what happens at x1, but I can certainly, between these 2 points, I can think about two things. I can think about change in x, and people often write this with a Greek letter delta x, and then change in y, right? You give me 2 points on a function, and I can see how much is the y value changing, how much is the x value changing. All right, and so the average rate of change of f on this interval, we can think about it as just change in y over change in x. Now, some of you are really bothered by those symbols. They're just symbols. It actually means the same thing as the change in y values is f of x2 minus f of x1, because that's what the y value here is f of x2, and the y value here is f of x1. So change in y over change in x. All right? And you can interpret this as you can interpret the instantaneous rate of change of f, and we should say at x equals 1, at x1, not x equals 1. So I'm interested in the instantaneous rate of change of f here at x1. You could also study it here, but I'm going to go here. So I can study the instantaneous rate of change of the function at a particular point as the limit, as the change in x goes to 0 of change in y over change in x. And this is the same thing as the limit as x2 goes to x1 of f of x2 minus f of x1 all over x2 minus x1. And this, of course, is precisely f prime of x1. All right, and so the point is, again, you can think about the instantaneous, the derivative, f prime of x1, is representing the instantaneous rate of change. Let's write this down. The instantaneous rate of change of y, which, by the way, y is f of x, with respect to x at your point x equals, I'll just say a here in general, but in this case it was x1. All right, let's just summarize here a couple of things. What's the takeaway? So going back to our example of rock chucking, the takeaway is suddenly this slope of the tangent line has meaning to us. We started out saying we wanted to find the slope of a function at a point, and you can interpret that slope as the instantaneous rate of change of your function at that point. That's what we said again here. The slope of the tangent line is the instantaneous rate of change of the function at the point. How fast are you changing? Then I introduced some other notation. I won't use this a lot, but I wanted you to be familiar with it. People will write change in y as delta y, change in x as delta x. You've probably seen that before somewhere when you were studying lines. And so if you write down all of this, in these symbols, let's see, let's just turn that off. If you write down the limit as change in x goes to 0 using all of these symbols, then you get out exactly the same formula for the derivative that we had before. So average rate of change, just a secant line. Instantaneous rate of change is a limit, and it spits out, it's a limit of the secant lines, and it spits out the slope of the tangent line. And then again, last time I'll say it, I want you to think about the derivative as representing the instantaneous rate of change of y with respect to x. So let's end this video here, and we'll do one more example.